Our course is all about switches, and switches work at what's called the data link layer of the OSI model. But in order to build networks with switches, we've got to look at layers both up and down from the data link layer. So we're going to look a little bit at the physical layer and a little more on the network layer of how this works. And so this first tutorial is just on how does basic network communication work. So what we mean is, let's look at a network that we have here. And let's suppose I want to get data from a machine in this network to a machine over in this network. So we basically want to transfer some type of data. What are all the elements involved and how does this all work? Well, there's three layers involved, and at the most basic layer, the lowest layer of the OSI model, layer 1, we're going to look at the physical. So here we've got three routers. These are all routers, which each create, two routers, which all create different networks. Over here we have what is called a token ring network, a little older network, and it electrically has a certain specification that it works at. And so the network cards in this network are responsible for converting the electrical signals that token ring uses into ones and zeros. Over here we have a network segment that's likely working on some type of Ethernet twisted pair. Common standards are one of the 802.3 standards. This is the IEEE standard designation. So a network card that's in a PC over here is different because it's going to convert the electrical signals that this network uses, which is different than token ring, into ones and zeros. And so it's very important at the physical layer, layer 1, that your network card properly interpret the electrical signals that's on the network. You could not take a network card from here and put it into a PC here and expect it to work. So for all the networks that we're going to use in our course here, they're all going to work at the proper physical layer. That's not generally an issue. Physical layer problems are typically things like broken cables, miswired cables, things like that, and we'll deal with that in some of the labs that we have coming up. The next layer we're going to look at, though, is what is called the data link layer. And this is the most basic layer that moves data between PCs on local networks. So this is a local network right in here. And the data link layer is responsible for moving information between computers. This is another local network. And here we have a third local network. So we're going to look at how the data link layer transfers data. And finally, we're going to look at the network layer, which is probably the one that most of the applications are going to use to transfer data. So we'll see how that all works. So we'll first look at the data link layer. Now what we have here is a very simple local network with three computers. And in order to move data from one machine to another, you need some type of designation or address for a machine. And at this layer, it's called the Media Access Control Address, or MAC address. Now, a MAC address has some characteristics. It is somewhat random. That is, doesn't really have any order to it. It is permanent in that it is burned into the firmware of the network interface card. Okay, so we have a PC here which has this long address. It is 48 bits of ones and zeros. I'm just going to draw a string of ones. And typically, we don't like dealing with 48 ones and zeros, so we typically break it up into groups of 4 and write the hexadecimal representation. So this would be a 9, this would be a C, and so on. We typically put colons. We have 2 digits, we put a colon, 2 digits, and another colon, so you'll sort of see it often written like this. But Cisco, in their packet tracer, put 4 together with a dot between them. So you'll see them in both these ways. But you'll see that this is somewhat random. Why would we want to do this? Well, in order to send information from one NIC to the other, we could send it globally, anywhere in the world. So we need everything to be uniquely identified. So we want every network card in the world to be unique. Generally, if we look at these 24 bits here, these identify the manufacturer. So this is the code given to whoever makes network cards. For instance, 000217 could be a code for IBM. And then typically IBM would, there should be a little colon in here, would then issue its own internal numbering system for all the NICs which it identifies. So there's no real logical structure for this globally. That is, we can't say that, okay, there's a network card in India. I sort of know how that network card is going to, what its address is. So that means it's difficult to send packets globally just using the MAC address. However, the MAC address does work very well on small local networks of, say, 50, anywhere from 2 to, say, up to 100 machines. Can work quite easily for delivering packets, information. Now, when we're moving data around a network, the physical layers is converting all the signals to ones and zeros, but there has to be a format for these ones and zeros. And at this layer, we call the information is broken up into chunks called frames. So when we're talking about data at this layer, which is layer 2 of the OSI model, we're talking about frames. And how is a frame constructed? A frame is constructed so that the first bits of information that come in from a frame are addressing information. Okay, and I'm going to use S and D for source and destination. I probably should reverse that. I'm not really sure which one goes out, but first, for the purpose of our talk, we'll assume that the destination is going out first. We have data that's in here. There's also some information in here which identifies the type of frame that it is. This will become more important when we start to talk about ARP and certain special data link layer frames. So we have the data, and at the very end there's some error checking which goes on to make sure the frame was received properly. Now, how do these addresses here work when a frame is sent? Well, there are 3 NICs here in these 3 PCs. They're all assigned these MAC addresses, which are burned into the NIC. So let's look at what does a network card do when it senses a frame, because here we have a hub, so any frame that's being transmitted, what a hub does is basically it just electrically works at it retransmits signals. So if a signal comes in here to a hub, it just electrically sends those signals out all the other ports. So a hub works at layer 1. Now we're not going to work too much with hubs, but it's good for the purpose of our talk here. Now what does a network card do when it sees a frame? Well, the first thing that a NIC does in processing ones and zeros is it looks at the frame and it looks at the destination address. That is, who's the frame being sent to? If the destination address in the frame equals my MAC address, then it processes the frame. Otherwise, it just ignores it. Now, there's one other special case. If the destination address equals what is called a broadcast. A broadcast MAC address. It also will process the frame. Now, what's a broadcast MAC address? Well, that's one with all ones in the MAC address. So if the destination address is FF, all Fs, and so on, it will also process the frame. It will store the source, that is who sent this information. It will do the error checking to make sure it received the frame properly, and then it will strip off what is called the payload. Different color here, which is the data in here. Now we'll also look at the frame type and see if, because of the frame type, it has some special processing to do at this level. But all network cards work this way, and therefore when information gets sent to any PC in any network, it must be in some type of frame format. A network card does not look at what are called IP addresses. It simply looks at the destination address, the MAC layer or layer 2 address in the frame to see if it's its own, matches its own, in which case it processes it, or it's a broadcast address, in which case it processes the frame, looks at the frame type, may have something to do there, and it strips out this payload, this data here, which then may be processed further. So that's what happens at the data link layer. Now we're going to look at the network layer, because most network communication programs such as ping, you could look at things like Skype, you can look at getting web pages from HTTP protocol. They all work using IP addresses. What we're going to find is that in any network that communicates beyond its own local network, it's going to also be assigned an IP address that you'll see here. Now, why do we use IP addresses? And what we're talking about here is IP version 4. We won't be talking about IP version 6. IP addresses were invented because it was very difficult to determine addresses, MAC addresses especially, for machines which are on distant networks. So IP addresses came and solved this problem. The whole IP address structure is hierarchical. Sort of a tree structure. And it becomes easy based on the IP address to determine where machines are. For instance, in this network here, it's been assigned 192.168.0.0, but because of the network mask, and we'll see what the mask means later, basically anything that is 255 is part of where the network is. So this part of this address identifies this whole network. The last part of the address here identifies machines, or what are called hosts. So in IP version 4, we have 4 what are called octets. Octet is 8 bits, so we have 32 bits. 32 bits that we're using for network addresses. And again, lots of ones and zeros that humans don't work very well with. So we break down 2, 3, 4, 5, 6, 7, 8. We take them in groups of 8. And this time we could convert them to hex, but we don't. The convention is to convert them to a decimal number. And so you'll get some number between 0 and 255. So in our example here, this might be 192, although this is not the binary for 192, and so on. At this level, when we talk about the network layer, we send data in what are called packets. So when we're talking about data flow and we're using IP addresses in our discussion, we're talking about sending packets. So for instance, ping, which is really what's called an echo request. I'm requesting another machine to simply return what I'm sending to it. So we'll call it an echo request. That's the data part of the packet. We're going to send this packet to another machine, which we know only by IP addresses. It's IP address. So let's suppose machine 1 wants to send to PC3 here. Well, again, I'm going to send an echo request, so the data part identifies what I want, what type of message I'm sending. So this is the data, or the message type. And I'm going to encapsulate that with some error checking. And I'm also going to put in the front of it some addressing. And just like with the frames, we're going to put a destination and we're going to put a source, but this time an IP address. So this destination address is going to be 192.168.0.4, and the source will be 192.168.0.2. Now, this is a packet. However, eventually this packet has to be sent in a local network, and we said that we can't send packets because network cards only look at frames. They only look at destination addresses and frames. So what happens is ping constructs this packet, and then the software in this PC has to then encapsulate it and create a frame. So what has to happen is we'll take this packet, which has some addressing, destination, source. This is IP addressing here, and an echo request in here, maybe a little checksum. And it's going to add to that or encapsulate that with framing information. And framing information here is going to be MAC address information, destination, source. So the destination MAC address that has to eventually be created will be this. So that will have to go in the destination. The source MAC address will come from here. The destination IP address will be this one, and the source IP address will be this one. And there'll be some error checking that's added to it. Now this frame gets sent out to the hub, and the hub simply rebroadcasts it on all its trunks. And it gets processed by the NIC in PC2, and it gets processed by PC3. So PC2 is going to say, I'm going to look at the destination MAC address. And does it match mine here? No, it doesn't. Is it a broadcast? No. So PC2 simply ignores the frame. PC3, though, looks at the destination, says, that matches my MAC address, and so I'm going to process that further. It looks at the frame type. I haven't shown the frame type in here. And it knows that it's going to send it up to some software in its driver that's going to be responsible for processing network layer information. So it basically strips off this packet and sends it on for processing in its PC. The ping application eventually gets this. Part of the processing is looking at the destination IP address. The destination IP address also matches its IP address. So again, it does not discard the packet. It looks at the packet, looks that it's an echo request. The ping program will give an echo response. It'll know where to send it to because it had the source MAC address, it had the source IP address, and so it can construct a frame to send back out to the hub, which gets sent here and gets sent here. Now the destination MAC address is going to be this one. So PC2 is, again, simply going to ignore the frame. This is going to process and get that echo reply. So what we've shown here is how a basic piece of information gets sent from one PC to another. We've discussed a little bit about the physical layer, about the necessity of the NICs all adhering to the proper IEEE standard that the local network is using. So it's going to convert those electrical signals to ones and zeros. We've talked about two types of addressing which is important: the MAC address and the IP address. The MAC address is burned into every network card. It makes every network card in the world unique. But it is not very logical. It's not easy to find a distant network MAC address machine. Therefore, IP addresses were invented. They're very hierarchical or have a tree structure. They're a logical structure, a logical way that we can number networks so that we can easily send packets from one network to another. That's going to be the job of routers, and we're going to look at that much later in another course. So based on this, there are a number of questions that you should be able to answer now. So what I'm going to ask you to do is to look at these questions and come up with some answers. You can discuss it amongst yourself. I don't just want cut and paste, but I want you to use your own words and see if you can sort of get these basic concepts solidified in your mind.